Hello, in this lecture we will find out the area of the green triangle. In the drawing we have a quarter circle. A or B is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units. Line segment AQ equals to 5 units in its length. And this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AQO. So we'll focus on the right triangle APQ and we'll implement on this right yellow triangle APQ the Pythagoras theorem. And according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the yellow triangle is AQ. Therefore, the square of the hypotenuse is AQ squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to PQ squared plus PA squared. Repeat again. In the yellow right triangle APQ, according to the Pythagoras theorem, AQ squared equals to PQ squared plus AP squared. AQ is 5, therefore AQ squared is 5 squared, that is 25. And it is equal to PQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9. Plus PA squared. So actually found out that according to the Pythagoras theorem, 25 equals to 9 plus PA squared. We subtract 9 from this equation and finally we get that 25 minus 9 is 16, so 16 equals to PA squared. We will take a root out of this equation and finally we find out that PA equals to the square root of 16, that is 4. So PA equals to 4 units in its length. I write it down in the drawing that PA equals to 4 units. Here this line segment PA is equal to 4 units in its length. So here we have A or B is a quarter circle, and we can easily complete the quarter circle to a circle, and then point O will be the center of the circle. We have rule number 2, that a perpendicular from the center of a circle towards any chord bisects the chord. Repeat on rule number 2. A perpendicular from the center of a circle towards any chord bisects the chord. Point O is the center of the circle. From point O we draw perpendicular to chord BC. So this equals to 90 degrees and this equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So the perpendicular OM bisects chord BC. That is to say, it divides this into two halves. The first half is BM and the second half is MC. And the force BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Or here, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. So actually you can implement rule number 2 in our drawing. From the center of the circle, that is to say from point O, we will draw perpendicular on chord PA. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PA as M. According to rule number 2, the perpendicular OM bisects chord PA. And because of the fact that PA equals to 4 units, it means that PM will be equal to 2 units, and the second half, MA, will be also equals to 2 units. In the next step, we will define the intersection point between perpendicular OM and line segment QA SN. We define this angle as theta. If you focus on this right yellow triangle AMN, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big yellow right triangle APQ, inside this right triangle, we have this angle that is equal to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we will prove that the small right triangle AMN is similar to the big right triangle APQ. Okay, so I write it down. The big right triangle APQ is similar to the small right triangle AMN. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is a common angle that belongs to both triangles. It is very easy to see that angle theta belongs to triangle AMN, and angle theta also belongs to the big triangle APQ. So we'll call angle theta two different names. If we relate to angle theta as it belongs to the big triangle APQ, then it will be defined as angle PAQ. Now we will relate to angle theta as it belongs to the small triangle AMN. Therefore, angle theta will be defined or will be called as angle MAN. Okay, both angles are actually angle theta. Again, it is a common angle that belongs to both triangles. Repeat again. Angle theta can be called as PAQ when we relate to angle theta as it belongs to the big triangle, and angle theta also can be called as angle MAN if we relate to angle theta as it belongs to the small triangle. So angle theta equals to itself. It is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle PQN equals to, in the big triangle, equals to angle MNA the small triangle, they are both equal to 90 degrees minus theta, therefore they are equal to each other. I repeat again. Angle PQN in the big triangle equals to angle MNA in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all three angles in the big triangle PQA are corresponding equal to all the angles in the small triangle MNA. Therefore the two triangles are similar to each other according to angle similarity rule. So I write it down. Triangle APQ, the big triangle, is similar, this is the sign of similar, to the small triangle AMN according to angle similarity rule. So what is angle similarity rule? Angle similarity rule means that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then actually you proved that the two triangles are similar to each other according to angle similarity rule. From the fact that the two triangles are similar to each other, we will derive that the following relationship exists between their sides. That PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is also equals to QA in the big triangle over NA in the small triangle. I'll write it down. PQ over PA over MA equals to PQ over MN, and it is also equals to QA over NA. I repeat again. PA over MA equals to PQ over MN equals to QA over AN. PA equals to 4 over MA, it is equal to 2, it is equals to PQ equals to 3 over MN, that is unknown, so we leave it as it is, and it is equal to QA is 5 over NA, that is unknown, so we leave it as it is. In conclusion, I found out that 4 over 2 equals to 3 over MN equals to 5 over AN. From this equation, we derive that 4 over 2 equals to 3 over MN. Write it down, 4 over 2 equals to 3 over MN. Four over 2 is 2, so 2 equals to 3 over MN. We multiply this equation by MN, and we get that 2 times MN equals to 3. We divide this equation by 2, and finally we will get that MN equals to 3 over 2, that is 1.5. MN equals to 1.5 units in its length. So I write it down in the original drawing that MN, 97 MN equals to 1.5 units in its length. From the same equation, we derive that 4 over 2 equals to 5 over NA. 4 over 2 equals to 5 over NA. Four over 2 is 2, so 2 equals to 5 over NA. We multiply this equation by NA, and we get that 2 times NA equals to 5. We'll divide this equation by 2. And finally we'll get that NA equals to 5 over 2. 5 over 2 is 2.5. NA equals to 2.5 units in its length. So I'll write it down in the original drawing that NA equals to 2.5 units in its length. NA equals to 2.5 units in its length. What is the length of QN? From the drawing, it is very easy to see that line segment QN equals to QA minus NA. Again, QA minus NA equals to QN. Okay, so I write it down. QN equals to QA minus NA. QN equals to QA minus NA. So QN equals to QA, that is 5, minus NA, that is 2.5. 5 minus 2.5 is 2.5. In conclusion, found out that the length of line segment QN is 2.5. QN equals to 2.5 units in its length. So I write it down. QN equals to 2.5 units in its length. We know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we will block the right green triangle AQO by a circle. So we'll copy the right triangle AQO and we'll block it by a circle. So actually, this is the right triangle AQO that I call from the original drawing. Now we will block this triangle by a circle. So inside this circle, we have peripheral angle AOQ that is equal to 90 degrees. I'll write it down. Peripheral angle AOQ equals to 90 degrees in its size. And we have rule number 5 that states that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I'll repeat again on rule number 5. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Peripheral angle, this peripheral angle ABC equals to 90 degrees, therefore it rests on the diameter of the circle. AC is the diameter of the circle. We implement this rule number 5 in our drawing. Because of the fact that peripheral angle AOQ is equal to 90 degrees, therefore it rests on the diameter of the circle. That is to say, AQ is the diameter of the circle. I write it down. AQ is the diameter of the circle. It is given us the question that AQ equals to 5 units, and the diameter of any circle is 2 times the radius, it is 2r. From this equation, we will derive that 5 equals to 2r. 5 equals to 2r. We will divide this equation by 2, and we get that r equals to 2.5 units. The radius of this circle equals to 2.5 units. This is the right triangle AQO. We copied this right triangle AQO from the original drawing. This is also the right triangle AQO. So we copy point N that is located on the hypotenuse AQ from the original drawing to our drawing. Yeah. So this is point N that I copied from the original drawing. Line segment AN equals to 2.5 units. So here AN equals to 2.5 units. line segment NQ also equals to 2.5 units, so I write it down. QA is the diameter of the circle. Line segment QN is located on the diameter of the circle and it is equal to 2.5 units. But the radius of the circle also equals to 2.5 units. Therefore, QN must be the radius of the circle. Likewise, line segment NA equals to 2.5 units, but the radius also equals to 2.5 units. Therefore, NA must be the radius of the circle is equal to 2.5 units. Okay, now we know that QA is the diameter of the circle. And we also know that the center of any circle, it is actually located in the middle of the diameter. Again, the center of any circle is located in the middle of the diameter. That is to say, it is located at the point where the diameter is bisected into two halves. So we have here the diameter QA, and actually at point N, the diameter is bisected into two halves. The first half is QN, that is equal to 2.5 units. The second half is NA, this is also equals to 2.5 units. Therefore, point N must be the center of the circle. Repeat again. The center of any circle is located at a point where the diameter is bisected into two halves. And at point N, the diameter is actually bisected into two halves. The first half is QN, that is equal to 2.5 units, and NA, the second half is NA, that is also equals to 2.5 units. Therefore, point N is the center of the circle. In addition, we can say also that the center of any circle is located at a point where the two radii touch each other. We have the radius QN and the radius NA, and the two radii touch each other at point N. Therefore, point N must be the center of the circle. So, we can conclude that point N is the center of the circle. We join points N and O together by a straight line. What is the definition of line segment NO? The definition of line segment NO, point N starts from, line segment NO starts from point N, that is the center of the circle. And ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. So NO is the radius of the circle, that is equal to 2.5 units. So here NO is the radius of the circle, that is equal to 2.5 units. In the next step, I will copy the right triangle AMO in the new page, and we will implement on this right triangle AMO the Pythagoras theorem. The length of side MA is 2 units. What is the length of side MO of triangle AMO? It's very easy to see from the drawing that MO equals to MN plus NO. Again, MO equals to MN plus NO. So MO equals to MN, that is 1.5, plus NO, that is 2.5. In total, MO equals to 1.5 plus 2.5, that is 4 units. So this is the right angle AMO that I copied from the original drawing. E by PT is a relation for Pythagoras theorem. According to this Pythagoras theorem, the square of the hypotenuse is AO square is equal to AM square plus MO square. So AO square equals to AM square. AM is 2, so AM square is 2 square, that is 4, plus MA plus MO square. MO is 4, therefore MO square is 4 square, that is 16. So AO square equals to 4 plus 16, that is 20. We take out of this equation, and finally we get that AO equals to the square root of 20 units. You can write down in the original drawing that AO equals to the square root of 20 units. AO equals to the square root of 20 units. Its length. In the next step, I will copy the right green triangle AOQ in the new page, and we will implement on this right green triangle AOQ the Pythagoras theorem. AO equals to the square root of 20 units, and the hypotenuse AQ equals to 5 units. So actually, this is the right triangle AOQ that I copied from the original drawing. By PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, AQ square equals to AO square plus QO square. So AQ square, AQ is 5, therefore AQ square is 5 square, that is 25, and it is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 square, that is 20, plus QO square. Here we subtract from this equation 20, and we get that 25 minus 20 is 5, and 5 equals to QO square. We'll take out of this equation, and finally we get that QO equals to the square root of 5 units. QO equals to the square root of 5 units. So I write it down in the original drawing that QO, this side QO equals to the square root of 5 units. Now it is very easy to find out the area of the green right triangle AOQ. The area of the green right triangle AOQ or AQO here the squared bracket is the sign for the area. It means the area of triangle AQO equals to the area of any triangle equals to the base of the triangle times the height to the base. The height must create 90 degrees with the base over 2. So here the base of the green triangle AQO is QO, and the height is AO. Why the height is AO? Because it creates 90 degrees here with the base QO. Repeat again. The base of the green right triangle AQO is QO, the height is AO over 2. QO equals to square root of 5 units. AO equals to the square root of 20 units. over 2. So here we have the algebraic identity that the square root of a times square root of b equals to the square root of ab. According to this algebraic identity, we get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 divided by 2. 5 times 20 is 100, so inside the root we're left with 100 over 2. The square root of 100 is 10, and 10 over 2 is 5. So finally found out that the area of the green triangle, the green right triangle AQO equals to 5 square units. I'll repeat again, the area of this green right triangle AQO equals to 5 square units. In the next step I will summarize the lecture. So in the drawing we have a quarter circle, AOB is a quarter circle. Inside the quarter circle we have line segment PQ that is equal to 3 units in its length. Line segment AQ equals to 5 units in its length. And this angle APQ equals to 90 degrees. Our mission is to find out the area of the green right triangle AOQ. So we focus on the right triangle APQ and we implemented in this right yellow triangle APQ the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the source of the perpendiculars. That is to say, AQ square equals to PQ square plus PA square. Repeat again. AQ square equals to PQ square plus PA square. AQ is 5, therefore AQ square is 5 square, that is 25. PQ is 3, therefore PQ square is 3 square, that is 9, plus PA square. We subtracted 9 from this equation and found out that 25 minus 9 is 16. So 16 equals to PA square. We took a root out of this equation and finally found out that PA equals to the square root of 16, that is 4. So here, 97 PA equals to 4 units. Then we can complete the quarter circle to a circle, and then point O will be the center of the circle. And we have the rule that a perpendicular from the center of the circle towards any chord will bisect the chord. Repeat again rule number 2. According to rule number 2, a perpendicular from the center of a circle towards any chord bisects the chord. The center of the circle is at point O. From the center of the circle we draw perpendicular to chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as M. So the perpendicular OM, according to rule number 2, the perpendicular OM bisects chord BC. That is to say, it divides this into two halves. The first half is BM, the second half is MC, and of course they are equal to each other. That is to say, BM equals to MC. So whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. In this case, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. So we can implement rule number 2 in our drawing. In our drawing, from the center of the circle, that is to say, from point O, we draw perpendicular on chord PA. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PA is M. So according to rule number 2, the perpendicular OM bisects chord B. The perpendicular OM bisects chord PA. That is to say, it divides this into two halves. Because of the fact that PA equals to 4 units, it means that the first half PA will be equal to 2 units and the second half MA also will be equal to 2 units. Then we define the touching point, the intersection point between perpendicular OM and chord QA as N. Then we define this angle as theta. So if you focus on the right triangle AMN, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the right big yellow triangle APQ, inside this triangle we have this angle that is equal to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Then we defined, actually proved that the small right triangle AMN is similar to the big right triangle APQ. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle APQ in the big triangle equals to angle AMN in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, is a common angle that belongs to both triangles, so angle theta equals to itself. So angle PAQ that is theta equals to angle MAN that is theta. So it is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle PQN in the big triangle equals to angle MNA in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we proved that all three angles in the big triangle are correspondingly equal to all the three angles in the small triangle, therefore the two triangles are similar to each other according to angle similarity rule. I repeat again, the big triangle APQ is similar, this is the sign of similar, to the small triangle AMN according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you proved actually that the two triangles are similar to each other according to angle similarity rule. From the fact that the two triangles are similar to each other, we will conclude that the following relationship exists between their sides. PA in the big triangle over MA in the small triangle equals to PQ in the big triangle over MN in the small triangle, and it is equal to QA in the big triangle over NA in the small triangle. I repeat again. PA over MA equals to PQ over MN equals to PA over AN. PA is 4, AM is 2, PQ is 3, MN is 2, QA is 5, NA is unknown. So from this equation we conclude that 4 over 2 equals to 4 over MN, 4 over 2 equals to 4 over MN. 4 over 2 is 2, so 2 equals to 3 over MN. We multiplied this equation by MN, and finally we found out that 2 times MN equals to 3. Then we divided this equation by 2, and finally we found out that MN equals to 3 over 2, that is 1.5. Here, line segment MN equals to 1.5 units in its length. From the same equation, we can conclude that 4 over 2 equals to 5 over NA. Here, 4 over 2 equals to 5 over NA. 4 over 2 is 2, so 2 equals to 5 over NA. We multiplied this equation by NA, and we found out that 2 times AN equals to 5. We divided this equation by 2, and finally we found out that AN or NA equals to 5 over 2, that is 2.5 units. Here, NA equals to 2.5 units in its length. What is the length of line segment QN? From the drawing it is very easy to see that QN equals to QA minus NA. Again, QN equals to QA minus NA. Repeat again, QN equals to QA minus NA. QA is 5 and NA is 2.5. NA equals 2.5. So QN equals to 5 minus 2.5, that is 2.5. So in conclusion, found out that QN equals to 2.5 units in its length. We actually know that any triangle can be blocked by a circle. Again, any triangle can be blocked by a circle. Therefore, we blocked the right triangle AOQ by a circle. So I copied the right triangle AOQ in a new page and we blocked it by a circle. Here, this is the right triangle AOQ, the coordinate of the original drawing, and we blocked this right triangle by this circle. In this circle we have peripheral angle AOQ that is equal to 90 degrees. And we have rule number 5 that states that We have rule number 5 that says that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. I repeat it again on rule number 5. According to rule number 5, any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. Here, peripheral angle ABC equals to 90 degrees, therefore it must rest on the diameter of the circle. AC is the diameter. You see that peripheral angle ABC rests on the diameter that is AC. We can implement rule number 5 in our drawing. Why? Because of the fact that peripheral angle AOC equals AOQ. This peripheral angle AOQ equals to 90 degrees. Therefore, it rests on the diameter of the circle. That is to say, QA is the diameter of the circle. QA is the diameter of the circle. We know that QA equals to 5 units, according to what is given as the question, from one side, but from the other side, the diameter of any circle is 2 times the radius, it's 2r. So from this equation, we will derive that 5 equals to 2r. We divided this equation by 2, and finally we found out that the radius of the circle equals to 2.5 units. Here, QA is the diameter of the circle, and the radius of the circle equals to 2.5 units. So this is the right triangle AQO. I copied this right triangle AQO from the original drawing, triangle AQO. Okay, so they are exactly the same triangles. So I copied point N from the original drawing to the same triangle AQN that we have AQO that we have here. So I copied this point N here, in the same triangle AQO. And we have only found out that line segment AN equals to 2.5 units, and line segment NQ also equals to 2.5 units. Okay? And because of the fact that the radius of the circle equals to 2.5 units, and NA also equals to 2.5 units, NA must be the radius of the circle. Why? Because it is located on the diameter QA. Likewise, QN equals to 2.5 units, the radius of the circle also equals to 2.5 units, therefore QN must be also the radius of the circle because QN is located on the diameter of the circle. Okay? Now, what is the center of this circle? We know that the center of any circle is located at a point where the diameter is bisected into 2 halves. Here the diameter is QA, and exactly at point N, the diameter QA that is equal to 5 units is bisected into 2 halves. The first half is QN that is equal to 2.5 units, and the second half is NA that is also equals to 2.5 units. Therefore, point N must be the center of the circle. In addition, we can say that the diameter of any circle is at the point where the two radii touch each other. And exactly at point N, the two radii, QN and NA, touch each other. This is another reason that point N is the center of the circle. In conclusion, we can say absolutely that point N is the center of the circle. We will join points N and O together by a straight line. What is the definition of line segment NO? Line segment NO starts from point N, that is the center of the circle, and ends at point O, that is the point of the circle itself. This is exactly the definition of a radius. So NO is the radius of the circle, that is equal to 2.5 units. You can write down here that NO is the radius of the circle that is equal to 2.5 units. In the next step, I copied the right triangle AMO in a new page and implemented in this right triangle AMO the Pythagoras theorem. Side AM of the right triangle AMO equals to 2 units. Instead, what is the length of MO? From the drawing, it is very easy to see that MO equals to MN plus NO. Again, MO equals to MN plus NO. Okay, MN equals to 1.5, NO equals to 2.5. Therefore, in total, MO equals to 1.5 plus 2.5, that is 4. So MO equals to 4 units. Okay. So actually, this is the right triangle AEMO that I copied from the original drawing. Here by PT is a version for Pythagoras theorem. So according to the Pythagoras theorem, in this right triangle, AOM, AO square equals to AM square plus MO square. Again, AO square equals to MA square plus MO square. AO square equals to AM square. AM is 2, therefore AM square is 2 squared, that is 4, plus MO square. MO is 4, therefore MO square is 4 squared, that is 16. So AO square equals to 4 plus 16, that is 20. We took out of this equation and finally found out that AO equals to the square root of 20 units. Here, side AO equals to the square root of 20 units. In the next step, I copied the right green triangle AQO in a new page and we implemented the Pythagoras theorem in this right triangle AQO. This is the right green triangle AQO that I copied from the original drawing. Side AO equals to the square root of 20 units. The hypotenuse AQ equals to 5 units. Okay. According to the Pythagoras theorem, in this right triangle AQO, AQ square equals to AO square plus QO square. Again, AQ square equals to AO square plus QO square. AQ is 5, therefore Q square is 5 squared, that is 25, and it is equal to AO square. AO is square root of 20, therefore AO square is square root of 20 squared, that is 20, plus QO square. We subtracted 20 from this equation, and finally we found out that 25 minus 20 is 5, that is equal to QO square. We took a root out of this equation, and finally we found out that QO equals to the square root of 5 units. Here, QO equals to the square root of 5 units. Now it is very easy to find out the area of this green right triangle AQO. The area of the green triangle AQO, the squared brackets is the sign for the area. This is the area of triangle AQO. Equals the area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. The base of the green triangle is QO and the height is AO. Why the height is AO? Because it creates 90 degrees with the base QO. This angle equals to 90 degrees. Again, the base is QO and the height is AO over 2. QO equals to the square root of 5 units. AO equals to the square root of 20 units. Again, QO equals to the square root of 5 units. AO equals to the square root of 20 units divided by 2. We have the algebraic identity that the square root of A times square root of B equals to the square root of A times B. According to this algebraic identity, we will get that the square root of 5 times square root of 20 equals to the square root of 5 times 20 over 2. 5 times 20 is 100. So inside the root we left with 100 over 2. So the square root of 100 is 10 and 10 over 2 is 5. So finally we found out that the area of this green right triangle AQO equals to 5 square units. So repeat again, the area of the green right triangle AQO equals to 5 square units. Okay, thank you very much.